Hello, I welcome you all in this course on power plant engineering. Now, from this lecture onwards, we will discuss about the direct energy conversion. We have already discussed the hydro power, thermal power, and nuclear power as well, and the combination of these power generations. And now we'll go in coming lectures. We'll go for direct energy conversion. So, in direct energy conversion, first is solar power, right? Now, before we discuss the solar power, I would like to discuss certain facts about the solar radiations. Topics to be covered, therefore, topics to be covered in today's lecture. First of all, about the sun, then solar constant, air mass, solar angles, equation of time, solar radiations, because these informations are required when you design a solar thermal power plant, right? So, first of all, let us know the sun out of which we are getting the power. Now, the diameter of the sun. Let us have some physical idea about the sun. So, diameter of the sun is 1.39 into 10 to power 6 kilometers. If you compare with the diameter of the diameter of the earth is 6400 kilometers. So, it is more than the 200 times. The diameter of the sun is more than 200 times the diameter of the earth. Distance from the earth. Distance of the earth is 1.5. It is exactly 1.49 something, but I have rounded off to 1.5 into 10 to power 8 kilometers. As you know, the velocity of the light is 3 into 10 to power 8 meters per second. If you calculate the time traveled by the light from sun to earth, so it is going to be 10 to power 3 meters, 10 to power 8 divided by 3 into 10 to power 8. 0.5 into 10 to power 3, it is going 500 seconds. If you convert this 500 seconds into minutes, it is going to be 8.3 minutes. This is the time the light takes to travel from sun to earth. Sun also rotates on an axis. As the earth and the moon, they rotate on their axis. Sun also rotate on its axis, and it takes 4 weeks time. In 28 days, it rotates on its own axis. The radiations of the sun, they go in all direction, and at a distance of this much, when earth is here, the angle rendered by the radiation line is 32 minutes. They are almost parallel when they are coming to the earth. Now, sun does not rotate as a solid body. Sun is not a solid body, so it does not rotate as a solid body. This equator, it takes 27 days, and polar region, it takes around 30 days. Because sun is like a fireball. It does not have any solid, any material in a solid state. All the materials are in gaseous state. The temperature of interior region of the sun is 8 to 40 into 10 to power 6 Kelvin. So, at this temperature, none of the material or the solid material will survive. Now, we will not go into the details with the of the sun. Now, sun is an energy source for us. So, what sort of energy you are getting from the sun, and what is the magnitude of energy we are getting from the sun? That is important here. So, if we consider sun as a black body, then a black body of 5777 Kelvin temperature. So, if we take a black body which is at 5707 Kelvin temperature, the same amount of radiations which are coming from the sun to earth. Now, the maximum, so sun radiations, they keep on changing with time. So, the maximum radiation 6300 Kelvin. So, if you want to have maximum radiation from the sun, the black body temperature has to be 66,300 Kelvin. Now, radiations coming from the core of the sun, they are in the form of gamma and X-rays. Gamma and X-rays. And their wavelength, because gamma and X-rays, they have a smaller wavelength. This wavelength keep on increasing when we move away from the center of the sun. Because when we are moving from the center to periphery, the wavelength of the radiations increases, right? And 90% of the energy in sun is generated x is equal to 0.23 r. 23% of the radius, 23% of the radius, 90% of the energy is generated. And if you move a distance 0.7 r, if you move 70% distance from the center, the temperature drops to 130 kilokelvin or 0.13 million Kelvin when you move 70% distance from center towards the periphery. And this is this zone which is 0.3, I mean 0.7 we have already moved. This 0.3 R is known as convective zone. And in this zone also the temperature falls around 5000 Kelvin. And density is 10 to power minus kg per meter. Density is very low. When the temperature is very, very high, the density is going to be very, very low, right? So, the outer convective zone of the sun is known as photosphere. And beyond the photosphere, there is a corona, and the density here is 10 to power 4 kg per meter cube. This is about the sun, and what we see mostly what we see, it is corona only. It is corona only. Now, there is a term which is known as solar constant. Solar constant is G, which has value of 1353 watt per meter square. It is the amount of radiation falling on the Earth's surface, right? While this radiation, when it is penetrating the Earth atmosphere, now this is the radiation which is falling on the Earth. When this radiation penetrates the atmosphere of the Earth, it also gets reduced. But outside the atmosphere, it is 1353 watts per meter square. Now, because Earth is not in the center of the orbit, sorry, the sun is not in the center of the orbit of the Earth, there is some eccentricity. That is why there is plus minus 3% variation in the value of G. Suppose any day you want to have the value of G is equal to G 1 plus 0.033 cos 360 n divided by 365. Now, suppose you want to have the value of GT on 1st July. So, 1st July is n is equal to 182. So, GT is equal to G 1 plus 0.033 cos 360 into 182 by 365. Now, if we take 360 cos of 360 into 182 divided by 365, it is minus point G and it is multiplied by 0.033. So, it is 1 minus 0.0329, right. So, again there is a variation approximately 3%. So, G is 1353 multiplied by into 1353, 1308 is equal to 1308, right. So, this is the variation of plus minus 3% due to eccentricity of Earth with the sun. Another term which commonly comes into the picture while we do the work on the solar energy, that is air mass. Air, suppose you are standing here on the earth, this is zenith, air is, sun is here at an angle theta. So, this distance versus this distance, the ratio is air mass. So, the air mass is the ratio of x, y, z. So, it's the ratio of x and y. Ratio on x and y is sec theta or 1 by cos theta, right. Second thing is, when the sun is here, it has to travel more distance. When the electromagnetic radiations or the light, when light is traveling or the radiations are traveling, we have two types of radiations. One is direct energy radiation, direct radiations, radiation directly falling on the earth. Another are diffuse radiations. When the radiations, they are scattered, and when they are scattered, they are diffused, and we get, so the total radiation is direct radiations plus diffuse radiations. DNI, direct radiations plus diffuse radiations. So, the sum of the direct radiations and diffuse total radiation is total radiation, right. So, due to this angle, further attenuation in the radiation takes place, and this intensity of the radiation reduces is equal to 1082 e raised to power minus 0.182 divided by sin theta. This is the formula of attenuation of radiation with the angle of theta. So, as I said, direct radiation or beam radiation they are direct, right, and another is diffuse radiation. They are indirect type of radiation. So, when we are sitting in the room and the windows are open, sunlight is coming to the room. This is by diffusion. It is not the direct light, it is the light through diffusion. So, the total radiations are the sum of these two radiations. Now, there are certain terms in solar energy. First is irradiance. Irradiance, it is expressed in terms of watt per meter square. It means energy falling on the first surface per second on per meter square area. This is known as irradiance. And another is irradiation. Irradiation is, it is not watt per meter square, it is joules per meter square. Energy falling on the earth's surface over a period of time, right. So, it is joules per meter square. This is known as irradiation. Another is radiosity. Radiosity, rate at which energy leaves the earth, right, and that is known as radiosity, and it is leaving the earth's surface by emission, and this is also terms watt per meter square. So, there are three things: irradiance, irradiation and radiosity. Now, let us talk about the earth. Earth is inclined on an axis by 27 degree, 47, or we say 27.5 degree, right, because the earth is inclined on the axis. When the sun ray fall, right, so more radiations are this we are getting here rather than here. For example, if you take a torch, if a beam of torch is lighting this and a beam of torch is coming from this side, right, there is a earth surface, let us say this is the earth surface, beam of torch is coming like this and the beam of torch is coming like this, it is covering more area because it is oblique, right, but energy intensity will reduce, here energy intensity will be high. So, the part of the earth which is inclined towards the sun, suppose sun rays are coming from this direction and axis of the earth is like this part the radiation will be high and this part the radiations will be less. Earth has equator right? It is 0, 0, 0. Then it has Tropic of Cancer. And there is Tropic of Capricorn. It is 23.5 degree. It is 23.5 degree. And these parallel lines, they are known as latitudes. If you look at the side of the earth, in the center of the earth, they are latitudes at every degree. So this is 23.5. So this line at 23.5 is latitude of 23.5. Okay. Then at 16.5 or 16.5, it is Arctic Circle, and here it is Antarctic Circle. They are around 66.5 degree, right? So when we move north or south, right? So there is a change in the latitude. Now there are longitudes also on the earth joining the North Pole and the South Pole. If you move along this longitude, the time will not change. But if you move along the latitude, the time will change, right? Earth rotates, in 24 hours by 360 degree. So if you take 360 degree by 24 hours and multiplied by 60 minutes, 4. It means if you move by 1 degree means 4 minutes. If there is a difference in the latitude of two places, if it is 10 degree, the time between these two places is going to be the 40 degree. Time difference is going to be the 40 degree. That is why when we move on, and there is a latitude, 0 latitude, which gives the Greenwich Mean Time. It passes through somewhere in England, and which has longitude, not latitude, longitude as 0. And then we move towards the east, and longitude, say for example, India is 68.07 east and 97 degree and 25 minutes east. That is from east to west longitudes of India. If you take the difference, this is 97, simply 97 minus 68. So it is going to be 29. 29 broadly, 29 into 4. 116, and you divide this by 4, 89, 89 or 89, 116 divided by 4, 29, right. So there is a time difference, local time difference from extreme east to the extreme west of the India is 29 minutes. But we have one standard time, and that is the average of these two, 68 plus 97. If you take average of these two, 68 plus 97 divided by 2, this is 82.5, 82.5 degree east. That is the longitude which passes through Allahabad, near Allahabad, right? And this gives the Indian standard time. If I want to have local time, for example, Roorkee longitude is 77 degree 53 minutes, right? And let us assume it to be 78 degree for the sake of convenience. Allahabad is 82.5 degree, right? So so the difference between Roorkee and Allahabad is 4.5 degree multiplied by 4, 18 minutes. So this is the time difference, local time difference between Roorkee and Allahabad, right? And this is the local time which is given by the watch. There is another time which is known as solar time. Solar time is different from the local time, right? Solar time is, it depends upon the sun, and there is a equation of time, we call an equation of time. Equation of time gives the difference between the local time and the solar time. So when we are taking time with the solar watch, this equation of time has to be taken into the account. Right. So as we have calculated the local time by changing by taking the difference in the longitude into the account, difference in the longitude multiplied by 4, this will give the local time. It depends whether we are going east or west. If we are going east to Allahabad, the say Allahabad it is 12 noon. So for example 12 noon. So in Roorkee it is going to be 12 minus 18, 11, 48, no 38, 11:38 a.m. There is a difference of 18 minutes. Sorry, this is 22, 42, not 38, 42, 11:42. So in Roorkee it is going to be the 11:42 a.m. That is the local time. A local time by the watch, but the local sun time is going to be different. Why local sun time is going to be different? Because when sun takes at the same longitude, when sun takes 24 hours to come back. Meanwhile, there is a movement in the earth also, position of the earth also, right? And if you take into the account, we are getting an equation of time, and equation of time is expressed as E 9.87 sine 2b minus 7.53 cos b minus 1.5 sine b. This is equation of time, right, where b is 360 n minus 81 divided by 365, right. So once now we will again, if we want to have value of E in July, we will take n as 182 and we will put the value of b in this equation, we will get the value of E. And this E will be added in the local time. This E will be added in the local time, and this will give us the solar time. Earth Sun angles also, first and the most popular angle is angle of declination. Angle of declination is defined by D, and it is the angle of the sun from the earth plane of the earth. This is equatorial plane and this is sun. So this is angle of declination. Because earth is inclined at a certain angle, earth is not, it is inclined at a certain angle. So this angle of declination keeps on changing depending upon the position of earth with respect to the sun, right. So for any day, the angle of declination D is 23.47 sine j day plus 284 divided by 365 into 360. This will give the angle of declination, and when it is this is angle of declination. When this is inclined, then this is angle of declination, because sun rays are coming from here. So this is angle of declination. So angle of declination is also used in calculating in the calculations related with the solar radiation, and it keeps on changing. And June 21st, summer solstice, it is called summer solstice. The angle of declination is maximum, right? And angle of declination is minimum on equinoxes. Equinoxes is March 21st and September 22nd September, right. In India, it comes out to be 22nd March and 23rd September, right. There is another angle which is known as azimuthal angle. So if you take the earth like this is north, south, west and east, then sun is here. So this angle is known as azimuthal angle. Sorry, this angle, movement from the north. So this angle is known as azimuthal angle. Okay. So, these angles, the information about this angle is required when we do the calculation related with the solar energy. Now, in the coming lectures, when we will discuss how to trap the solar energy, we will be discussing more about the solar angles on the earth. That is all for today. Thank you very much.